Hi, in this video I would like to present you a mini conference I was supposed to give at my university in Spain, La Universidad de La Laguna. I wasn't able to give that conference because of the current sanitary situation, namely the COVID-19 outbreak. The purpose of this video is to give you a few basics to get around the sky. I find it sad that knowledge of the sky isn't part of our general literacy. It isn't taught at school. I myself was late to it. And I mean, picture this. Whether on a given day you've gone to the beach or to the mountain or you've opted to stay home, as you raise your gaze, what you see above you is the exact same thing, the same patterns of little dots of light. It's no wonder Aristotle thought that the heavens were eternal and perfect. Even as the world around you can change dramatically, the world above you remains the same. Okay, so let us start by talking about Polaris. Already in the first picture of this presentation, you can see that Polaris will play a central role. It is going to be our reference point in the sky. It is also called the North Star. So how do you find Polaris? First, you have to face north. After all, it is called the North Star. And then you have to look above the horizon by an angle equal to your geographical latitude. In the case of the Canary Islands, it is 28 degrees. So given that I am 1.86 meter tall, in order to achieve that angle, I must place my head some 87 centimeters above the ground. And then my body will make a 28-degree angle with the ground. And so my body will point to Polaris, and my body will also be aligned with the Earth's rotation axis. And if you remember, this is exactly what the King of Pop was trying to achieve with this famous dance move. So as we all know, Michael Jackson's success was tremendous and international. It inspired many lookalikes from around the globe who rose to the challenge of copying his moves. But you know, some had it easier than others. Like if you are a Michael Jackson lookalike living up north, like at the North Pole, in order to achieve this move, you will only have to stand upright. Yeah, because Polaris is right above your head at the zenith. There is, however, a location on Earth that is even more advantageous. Imagine you are on the equator, let's say in Ecuador. In order to perform this dance move, in order to align your body with the Earth's rotation axis and to point at Polaris with your body, you only have to lie down. Yeah, it's as easy as that. Okay, so this is how you locate Polaris. Now, why is Polaris so special? As you can see in this animation, stars move across the sky as time passes, except for Polaris here, which is in the middle, which appears to stay put. Actually, if you look at it very carefully, you will see that it moves by a tiny little bit, but not much at all. Okay. So, Polaris will be our fixed reference point in the sky. Now, how do you locate the other stars with respect to Polaris? You can see on this long exposure photo the paths that the stars follow. Can you see how those seem to be circles centered on Polaris? That gives us a nice way of locating a star with respect to Polaris, namely the North Pole distance. The North Pole distance is simply the distance in degrees of a given star to Polaris. So in the case of Kochab, one of the stars making up the Little Dipper over here, the North Pole distance is about 16 degrees. If you go to Calf in the constellation Cassiopeia, the North Pole distance is roughly 31 degrees. And if you go to Shara, I think it was, quite a bit further, the North Pole distance is 49 degrees. Now, I should mention here that The NPD, as it is known is in the jargon, is not the most common measure. What is used normally is the declination, which goes from the celestial equator instead of from Polaris. I find it to be a bit less intuitive, but just for your general knowledge, you should know that usually we use the declination, which you can get from the North Pole distance just by subtracting the NPD from 90 degrees. So in the case of Kochab, that would be 74 degrees, declination of 74 degrees. For Kaf, it would be 59 degrees, while for Chara, it would be only 41 degrees. Okay, enough about space. Let us now talk about time. Let's go back to this animation. So you see that the stars move across the sky, and if you were to wait long enough, namely 23 hours, 56 minutes, something like that, and so not quite 24 hours, you would see that any given star would have come back to its initial position when you started to observe the sky. This is the length of a sidereal day, okay, when the stars come back to their initial position. And here you can see that you can use the sky as a clock which will give you sidereal time. Now, how do you get sidereal time? Let me give you two nice ways of figuring out or at least estimating sidereal time. Let me introduce to you the celestial clock. So the celestial clock is centered on Polaris, and it has two unusual features. The first is that it has 24-hour tick marks instead of 12. And the second is that its hands go counterclockwise, which is admittedly quite unfortunate for a clock. But as you can see on that animation, the stars go counterclockwise, all right, around Polaris. Okay, and the stars will be our clock hands. All right. So the first way that you can estimate sidereal time is to locate Kaf in the constellation Cassiopeia. Imagine a clock hand pointing at Kaf and just read the sidereal time. So here it is about 22 hours, right? Because this is 18 and this is 0, also known as 24. So here we are at about 24 hours. The second way of figuring out sidereal time is to see the Little Dipper here as a clock hand, okay? And then you have to be careful to add 15 hours to your reading. Okay, those offsets, you can see that even Kaf has a very small 9-minute offset that I have neglected when I talked about it. Those offsets correspond to the right ascensions of the object, but this is a technical detail that isn't part of the scope of this introductory video. Okay, so you can see here it's very rough, right? So this is 6 hours and we are increasing counterclockwise. So let's say this is 7 hours. This is maybe a bit less than 7, but anyway, you add 15 and you get roughly 22 hours for your sidereal time again. Okay, up to now we have assumed that we knew our location on Earth and where North was in order to find out about the sky, in order to find Polaris, for example. Let us now go into reverse and see how the sky can help us ascertain where we are on Earth. So, latitude, how far above the equator you are. So, this video is only for the northern hemisphere folks. I apologize to the southern hemisphere people. So latitude is quite easy. Just locate Polaris in the sky. As a bonus, it will tell you where North is, and see how far it is above the horizon, okay? And that angle, as we mentioned before, will be your latitude. Longitude is quite trickier, and longitude was the very problematic part for navigators centuries ago, who had to figure out where they were in the ocean without the GPS system. Longitude was the tricky one to figure out. This formula allows you to determine your longitude. Let us for now assume a modern setting with all of current technology at our disposal. So this Greek letter lambda stands for longitude, and on the other side of the equal sign, the first term is theta naught. It is an offset given to you by the date. So I won't get into details, but if you want to know, it is roughly the number of days that have elapsed since the autumnal equinox times 4 minutes approximately, all right, which you then have to convert to degrees. Okay, the next term is given to you by the position of the stars. It is the sidereal time. So you get that by looking at the sky and seeing where the stars are on your celestial clock. This K is a constant, which has to do with the fact that the sidereal day and the solar day don't have quite the same length, all right? But I just give it to you as a gift. You can write it down. So I won't get into the details of that either. Finally, that T is universal time, and you can get it from your wristwatch, which you have carefully set to Greenwich time. Now, that last term, that T, was the tricky thing to get for navigators, because it's not hard to keep track of the date. You know, they knew much better than we do how to deduce things like sidereal time from looking at the sky. I mean, provided a clear sky, but let's assume a clear sky, right? They knew the value of K, which to my knowledge hasn't changed in centuries, or maybe even tens of thousands of years, I don't know. And T was very hard to keep track of because they didn't have digital watches, right? If you think about one of the options available at the time, namely the pendulum clock, a pendulum clock cannot work on a boat because the boat is tumbling, and this tumbling disturbs the oscillations of the pendulum, which can no longer be relied upon to keep time. All right, so we've reached the end of this presentation. I have used screenshots from those two apps, Stellarium, which is available on your computer, and Starwalk 2, which is available on your smartphone. I think they are great tools that can help you in your study of the sky. I would like to thank the University of La Laguna, and I send my warm thoughts to the organizing committee of the COEFIS. And to you all, I wish you a very nice day. Bye-bye.